This lecture is part of an online mathematics course on group theory and will be mostly about nilpotent groups. So we'll start by looking at groups of order 16 because we've classified all the groups of order less than 16. Well, we're not actually going to give a proof of the classification because this is kind of a bit tedious, but let's just list them to see what we get. So we're going to list all the groups of order 16 we can think of. First of all, there are 5 abelian groups that we considered in the previous lecture, and these correspond to the fact you can write 16 as a product of numbers in the following ways. 4 times 2 times 2, 2 times 2 times 2 times 2. So we can get 5 abelian groups as product of cyclic groups of these orders. Then there are 2 products of z modulo 2z with either the dihedral group or the quaternion group of order 8. Then there are several groups. There are 4 non-abelian groups with an element of order 8. And these are as follows. We get a generalized quaternion group, this is the same as the binary dihedral group, dihedral group of order 16, which means you take the dihedral group of order 8 as a group of rotations and take its double cover in the group S3 of quaternions. And then there are 3 groups that are semi-direct products of z modulo 8z by z modulo 2z. So these are generated by an element A with a to the 8 equals 1, and an element B with b squared equals 1, generating these 2. And then b to the minus 1 can be a cubed, a to the 5, or a to the 7. And if it's a to the 1, we just get an abelian group, of course. A to the 7 is the dihedral group. This one here is called the semi-dihedral group. And this one here is just nameless. Next, we have various semi-direct products. Of various groups, and these semi-direct products are as follows. We've got a group z modulo 4z, semi-direct z modulo 4z, with z modulo 4z acting non-trivial on this. We've got a group z modulo 2z times z modulo 2z, semi-direct product z modulo 4z. And there's a group z modulo 4z times z modulo 2z, semi-direct product z modulo 2z. And there's frankly not a lot of any great interest to say about many of these groups. We can make some minor comments. This is sometimes called the Pauli group. And in quantum mechanics, we have several matrices called the Pauli matrices. Oops, that should be a 0. 0 minus I 0. And 1 minus 1. And we can also add the identity group. And we can take all these 4 groups and multiply them by power of I, and that gives us 16 matrices forming a group, and that's this group here. I mentioned earlier that we can sometimes distinguish groups by counting the number of elements of various orders. And that fails for this group, because if you take, I think it's this group, I hope I've got it right, and this group here, these are both non-abelian, and they both have 3 elements of order 2 and 12 of order 4. So you can't distinguish these groups by counting the number of elements and seeing whether they're abelian or not. And this is actually fairly typical of groups of order 2 to the power of something, or for that matter, p to the power of something for p odd. You start to get large numbers of groups, and it's kind of hard to say anything very interesting about any particular group. The groups of order 16 are all nilpotent. I covered nilpotent groups in an earlier lecture, but since I can't assume that anybody either watched or remembered that lecture, I'll just review nilpotent groups. So you remember a group G is called nilpotent if you can kill it by repeatedly killing the center. So we take G0 as a group, as our group, we put G1 equals G0 over the center, and G2 equals G1 modulo the center of G1, and so on. And if Gn is trivial, the group is called nilpotent. And we saw earlier that groups of order p to the n for p prime is always nilpotent. And let's just recall the proof. All conjugacy classes have order a power of p, because the size of the conjugacy class is the size of an orbit of the group, so it must be the index of some subgroup, which is a power of p. So the size is equal to 1 or is divisible by p. Now the union of all the conjugacy classes is G, so the sum of the orders of all conjugacy classes is divisible by p. So the number of conjugacy classes of size 1 must be divisible by p, because it's just the order of G minus all these other conjugacy classes. So the number of conjugacy classes of size 1 is divisible by p. Well, a conjugacy class of size 1 is just an element of the center, where the center is something that commutes with all elements in G. So the center must be non-trivial because its order is divisible by G, so you can kill off the center to get a smaller group, and then by induction you can keep doing that. We also notice the product of two nilpotent groups is nilpotent. This is very easy, so I won't bother giving a proof of it. So we find that any product of P groups is nilpotent. So, and we're going to show that conversely, any finite nilpotent group is a product of P groups. I'm just going to talk about finite groups for most of the rest of this lecture, so I'll just implicitly assume they're finite. And to show that, so we've shown that a product of P groups is nilpotent. To show that a nilpotent group is a product of P groups, it's useful to introduce a third condition, that all Sobolev subgroups are normal. This means there's just one Sobolev P subgroup for any prime P. So what we're going to say is 1, 2, and 3 are equivalent for finite groups. So this means that for finite groups, being nilpotent is almost the same as being a P group, because taking a product of groups is a fairly trivial operation. unfortunately, this doesn't really help a lot with studying nilpotent groups, because it turns out that P groups are such a mess that the only way to study P groups is to use the fact that they're nilpotent. But anyway, so we've proved that condition 1 implies condition 2. So now let's show that 2 implies 3. So condition 2 says that they're nilpotent, and condition 3 says that Sylow subgroups are normal. And to do this, we're going to use induction on the order of the group. So pick some element G in the center of G with G to the P equals 1, where P is prime. So we're picking an element of order P in the center, and we can do this because the group is nilpotent. And we look at G modulo the group generated by this element. And G modulo P is still nilpotent, so all Sylow subgroups of G over P are nilpotent by induction. Here we're using the fact that if you've got a nilpotent group and you quotient out by something, then the result is still nilpotent, which is easy to check. And now we look at the Q Sylow subgroups of G. So suppose Q is equal to P, then a Sylow Q subgroup of G over P is normal, and the inverse image in G is a Sylow Q or equals P subgroup of G, and the fact that it's normal in here shows that its inverse image is normal. Now suppose Q is not equal to P, and pick a Sylow Q subgroup of G over P. And we look at the inverse image. When I say pick the Sylow subgroup of G over P, sorry, there's only one of them, and look at the inverse image in G. So the inverse image has order P times Q to the n for some n, where Q to the n is the largest power of Q, dividing the order of G. And this has a center of order at least P, because the group of order P is generated by this element in the center, and it has a Sylow subgroup of order Q to the n. However, this Sylow subgroup must be normal, because the only conjugates of it would be conjugates of it by elements of the center, and the center just fixes any Sylow subgroup. So the Sylow Q subgroup of this group is unique, and it must be the Sylow Q subgroup of G. So we've shown by induction that if a group is nilpotent, then all Sylow subgroups are normal. Finally, we show that 3 implies 1. So you remember 1 says that it's a product of P groups, and 3 says that Sylow subgroups are normal. So we want to show that if G has the property that all Sylow subgroups are normal, then it's a product of P groups. And what we do is we pick Sylow subgroups P and Q. So this is going to be a Sylow P subgroup for some prime P, and this is going to be a Sylow Q subgroup. And we're going to take P not equal to Q, and the main point is that P and Q commute, meaning every element in the group P commutes with every element in the group Q. And let's look at this. Suppose A is in P and B is in Q. Then look at A, B, A to the minus 1, B to the minus 1. And we notice that this is in Q because Q is normal. So this is in Q. And similarly, A, B, A to the minus 1, B to the minus 1. Well, this bit is in P because P is normal. So this element is also in P. So A, B, A to the minus 1, B to the minus 1 is in P and Q. But P and Q, the intersection is just trivial because this is a P group and this is a Q group, and P is not equal to Q. So any element in this intersection would have order of power of P and order of power of Q, so it would have to be 1. So AB equals BA. All the Silov subgroups for different values of P and Q commute with each other. Now we know by the Silov theorems that there is a Silov P subgroup for every prime P. These subgroups, we've just shown these subgroups all commute with each other, and from this it follows very easily that the group is just a product of these P Silov subgroups. So that shows that a group being nilpotent, a group being a product of P groups, and a group having all its Silov subgroups normal are all equivalent. So next lecture we will move on to groups of order 18 and discuss wreath products.